So effusion and diffusion are what we're going to be looking at during this lecture. And gas diffusion is basically the mixing or the random mixing of molecules of two different gases or two or more different gases by virtue of their basic kinetic energy. So gas diffusion, if you have two different gases in two different containers and you remove a separation that separates the two gases from one another, basically diffusion will naturally occur because those particles of gases are in motion. And Graham's law, which is the equation right here, allows us to interrelate the rate of diffusion to the molar mass of the gases in question. So we can compare two rates of diffusion and subsequently figure out something like a molar mass. Or we can take our molar masses and figure out the relative rates of diffusion. So what you need to pull away from this is that basically the lighter your gas is, the faster the diffusion process will happen for that specific gas. And on the flip side of that, the heavier the gas is, the more slowly it's going to move, or the slower it's going to diffuse. As you may recall, gas effusion is basically when a gas escapes a pressurized compartment, like a tire or something like that, into another container or another environment through a small opening. So gas effusion and diffusion both are referring to the movement of gas particles. Now let's go ahead and let's look at the question we have here. It says that nickel forms a gaseous compound of NiCOX. Okay, and they want us to figure out what the value of X is, given that under the exact same condition, methane is going to effuse 3.3 times faster than the NiCO compound. Okay, so how are we going to interrelate these to one another? So we were initially told that the rate of our first gas, which in this case I'm going to mark as the methane, is basically 3.3 times faster than the rate of our second gas, which I'm going to label as this one here. Okay, so we've been given the rate of 1 with respect to the rate of 2. Okay, we also know the molar mass of number 1 because we know that methane has a molar mass of 16 grams per mole. So if we take Graham's law and basically rearrange it and solve for M2, basically we take R1 over R2, that's going to equal the square root of M2 over M1. Okay, if I want to figure out what M2 is, I'm going to square both sides. That's going to give me, I'm going to put that up here, R1 over R2 squared being equal to M2 over M1. Okay, and then if I want to get M2 all by itself, because that's the one that I don't know, basically I'm just going to cross multiply, and basically my M2 is going to be equal to my M1 times R1 over R2 squared. Okay, so we know some of these values, but let's go ahead and plug in the ones that we do know. So M2 is going to be equal to 16 grams per mole. Okay, and we're going to multiply that by R1, which we know from right over here is equal to 3.3 times R2. Okay, so 3.3 times R2. Okay, and that's all over R2 squared. Okay, and if we cross out the variables that are constant, so R2 divided by R2 is going to give you 1. So really what M2 ends up being equal to is 16 grams per mole times 3.3 squared, okay, which if we calculate that out gives us 174.2 grams per mole. Okay, so that gives us the mass of our NiCO compound. So in order to figure out what X is, we're going to consider the masses that we do know in the compound of the NiCO gas. So what we're going to do is take the known molar mass that we just calculated of the total NiCO complex, and we're going to set that equal to what we know from the unit. So we know the mass of nickel, and we know we only have one atom of that. Okay, and we're going to add that to X times 28, which is the mass of carbon and oxygen combined. Okay, so if we go ahead and manipulate this and solve for X, that's going to give us 4.1, which is approximately equal to 4. So our X value is 4, and our NiCO complex has this formula. Okay, so as you can see, we can get a lot of information from Graham's law here. Okay, when you're labeling this stuff, make sure that you're keeping track of which variable is which, and that they should be basically on opposite sides, or one should be on the top, the other should be on the bottom. Okay, so the rate of one should be on the top if the molar mass of one is down at the bottom here, and vice versa. So it doesn't matter if the 2 or the 1 is on the top, it just has to be opposite to the other variable that's in the equation. Okay, so we recently talked about kinetic molecular theory and the assumptions that we make based on ideal behavior of a gas. And so now what we're going to look at is basically the deviations from ideal behavior, and you know what comes into effect to create those deviations. Okay, so when we're assuming that something is an ideal gas, we assume that the molecules themselves don't occupy space. And the reality of it is that molecules do occupy space. You know, they're three-dimensional structures, so of course they do. And this very, very small volume will actually end up resulting in a slightly higher pressure than you would expect, because there's slightly less room for them to move around in the container, and subsequently, you know, they bump against the side of the container a little bit more, and you get a higher pressure value. Now, when we're at low pressure, we don't really see this deviation. It's not really a big deal. That's why we can make those assumptions. However, when we start to do chemistry or basically run reactions or do processes at really, really high pressures, this difference, or this volume of those particles, starts to make a bigger impact in terms of the pressure. So as we have said previously, you know, ideal behavior works for most of the conditions in which we look at gas calculations, but the reality of it is that gases do occupy volume, they do take up space, and so that you will see conditions in which there will be a deviation in pressure based on the fact that those molecules actually do take up space. Okay, so if we look at intermolecular forces, or the attraction between the particles, you know, when we're talking about ideal gases, we make the assumption, as we said earlier, that there aren't any intermolecular attractions that occur. However, in real gases, there are slight attractions, and these slight attractions have to be overcome by some kinetic energy. And so because there's energy being put into separating out those particles, because they do have attractive forces, you're not going to have those particles moving around and hitting the surface of the container as frequently, and so you end up with a slightly lower pressure than you would anticipate. And once again, there has to be kind of a more extreme type of situation in order for you to see these deviations, and that happens at very low temperatures. Okay, so when the particles are moving really slowly, there isn't a lot of kinetic energy to overcome these intermolecular forces, or at really high pressures when the particles of gases are being kind of pressed together, and their opportunity to interact in that intermolecular fashion becomes more readily applicable. So the van der Waals equation that you see here basically accounts for the corrections that in both pressure and volume that we just talked about with respect to gases actually behaving in a real way versus in a ideal way. Okay, so we have two new factors here, as you can see. We have our value here, which accounts for the attractive forces that occur between molecules of real gases. And this factor right here actually accounts for the volume that the particles of gases in real gases actually take up. So really this is just PV equals nRT, but we've corrected the values with respect to our pressure and our volume. So basically we would treat this calculation or this equation the same way we would treat the PV equals nRT equation. However, in that situation, or in this situation, our values of A and B are actually pulled from van der Waals constant charts. And you would subsequently go and look up that value for the specific substance you're doing your calculation for. So if you're doing it for helium or hydrogen or oxygen, whatever gas you were looking at, you would find the van der Waals constants for A and B and subsequently plug them in and basically carry your calculation out in the same way you have in the past. So it's just an extra step and you're making a small adjustment. There's a small adjustment in your math, but overall it's the same approach.